All right, let's talk about something really fundamental today. Just look around you for a second. The frame of the building you're in, maybe, the engine in your car, even just the tools in your kitchen drawer. And, well, even inside us, right? The iron carrying oxygen in our blood. It's just everywhere. It's so fundamental to, like, everything we do. We barely even notice it sometimes.
Yeah, it's amazing when you stop and think about it. It's so common now. But have you ever actually paused to wonder, okay, where does this stuff, this iron, really come from? Like the actual atoms, where were they first made? And maybe even more interesting, how did humans way back when first get their hand on it? To start making things. It's quite a story.
It really is.
Yeah.
And that's basically our mission for this deep dive. We're going on a journey starting way out there in the heart of stars, all the way down to the very first tools people actually held. And I think you'll find there's a really surprising twist, a real aha moment about how we first started using iron here on Earth. So let's start way out, light years away.
Yeah.
Okay, so when we talk about where elements come from, iron, gold, carbon, even just hydrogen, we're talking about stars, aren't we? Those, huge glowing balls of gas and dust out there in space.
Precisely. Yeah, the ultimate forge, the place where elements are made, is deep inside stars. We're talking conditions that are, well, hard to grasp. In the core, temperatures hit something like 15 million degrees Celsius. It's, almost impossible to properly picture that kind of heat.
15 million degrees. Wow. Okay, so what's actually happening inside there at those temperatures, that creates new elements.
So under that intense heat and enormous pressure, the nuclei of atoms, the very centers of atoms, they don't just bounce off each other. They actually slam together hard enough to stick, to fuse. And this process, nuclear fusion, takes lighter elements, like hydrogen, smashes them together and makes slightly heavier ones, like helium. And the crucial part is, when this happens, it releases a huge amount of energy. That's literally what makes stars shine. It's the energy pushing outwards, stopping the star from just collapsing under its own gravity.
Right, so fusion powers the star, but it's also like an element factory inside. Now, not all stars are the same size, are they? Does the size, the mass, change what elements they can make?
Oh, absolutely. That's a really critical point. A star's mass basically decides its whole life story, including what it can cook up inside. Our sun, for instance, it's kind of average size. It's busy fusing hydrogen to helium now. Later, it'll fuse helium into carbon and oxygen. But to get all the way to iron, you need the real heavyweights, stars that are, say, at least 5 times more massive than our sun. These giants have enough gravity, enough pressure deep inside to really push that fusion process much, much further. So inside these massive stars, fusion keeps going. It builds heavier and heavier elements, kind of in layers, like an onion. Hydrogen fuses to helium in the outer layers, then deeper in, helium fuses to carbon, carbon to neon, oxygen to silicon, and so on. And each step, each new fusion reaction keeps releasing energy. That outward pressure keeps the star stable, balanced against gravity.
Okay, so they're building up these heavier elements layer by layer, releasing energy the whole time. But does it just go on forever? Can a star make like every element in the periodic table this way? There has to be a limit, right?
This is where it gets really interesting. And it's the absolute key to understanding iron. No, it doesn't go on forever. This energy-releasing fusion process, it hits a wall. And that wall is iron, specifically iron 56. You see, fusing lighter elements into iron, like silicon into iron, does release energy. That's why stars make so much of it. But, and this is the crucial bit, if you try to fuse iron into something heavier, the physics flips. Instead of getting energy out, you actually have to put energy in. Think of iron 56 as being like perfectly stable. It's the most tightly bound nucleus there is. Trying to add more to it or break it costs energy. So for the star's energy production, iron is the end of the road.
Wow. So iron is like the ultimate ash from the stellar furnace. It's so stable, the star can't get any more juice out of it by fusing it. So what happens then when the core of one of these massive stars fills up with iron? That sounds problematic for the star.
Problematic is an understatement. It's catastrophic. Once that core is mostly iron, the fusion reactions that were releasing energy just stop. And without that outward pressure fighting against gravity, the star's core collapses incredibly fast, like less than a second. And this incredibly rapid collapse triggers this bounce back, this enormous explosion, one of the most violent events in the cosmos.
A supernova.
A supernova, right. We hear that word, but understanding why it happens, because of iron, that really clicks. the ultimate fireworks show.
Totally. And this explosion, it's mind-bogglingly powerful. It doesn't just scatter that iron core everywhere. The intense heat and pressure during the supernova itself, that's where all the elements heavier than iron get made. Gold, silver, uranium, all that stuff. Then all these newly made elements, plus all that iron from the core, get blasted out into space. They mix into gas clouds, and eventually they become the raw materials for new stars, new planets. And, well, us. The iron in the Earth, the iron in our blood, it's literally stardust from these massive stars that exploded billions of years ago. Okay, wow. So exploding stars seed the universe with iron. Got it. But let's bring it back down to Earth, literally. Iron is, like you said, super common in the Earth overall, mostly deep in the core. But finding actual metal iron, pure iron, just lying around on the surface, that's pretty rare, isn't it? Because it rusts so easily.
That's a really important distinction, yeah. Earth has tons of iron. It's the most common element by mass, mostly in the core. But up here, on the crust and surface where we live, it loves to react with oxygen, with water. It forms iron oxides, basically rust, or it gets locked up in minerals. So finding a chunk of pure metallic iron, naturally, very unusual.
And that must have been a huge challenge for early humans, right? If the pure metal is rare and it rusts away, how did people even start using it? I mean, it eventually defined a whole era, the Iron Age. But getting started seems tricky.
It's a great question. Think about the metals people used earlier, like copper or bronze, which is copper mixed with tin. Humans figured out how to get those metals out of their ores, how to smelt them, using relatively simple fires or furnaces. You needed temperatures around, say, 1,000 degrees Celsius. But iron ore, to get metallic iron out of that, that's a whole different level. You need way higher temperatures, around 1,500 degrees Celsius. That's about 500 degrees hotter than for copper. It's a big jump in technology.
500 degrees hotter. Yeah, that doesn't sound easy to achieve in, say, 4000 BC. So mastering iron smelting, getting iron from rocks, that was a really advanced process. It took centuries, right?
Wow.
We see the first hints around 3000 BC in places like Mesopotamia, maybe Syria. But it didn't really take off and spread widely until much later, maybe with the Hittites, around 1500 to 1200 BC.
Okay, so here's the puzzle we've been setting up. This is the core question. If getting iron out of the ground, smelting it, was so difficult and needed technology that came relatively late, then how on earth did the very first humans get their hands on usable metallic iron to make the first iron tools, the first weapons, before anyone knew how to smelt it? Where did that initial iron come from?
And this is it. This is the aha moment. The very first metallic iron used by humans. It didn't come from Earth at all. Not from furnaces they built. It came directly from meteorites. Iron that literally fell out of the sky from the same cosmos where it was first made.
Whoa. Okay, wait. Meteorites. Seriously. That is surprising. So that makes perfect sense now. We were saying pure metallic iron is rare under the surface because it rusts. But iron meteorites, they are chunks of metallic iron, often mixed with nickel. They survive the trip through the atmosphere. They're like cosmic metal deliveries, already processed, ready to use.
Exactly. They're natural lumps of metal alloy, mostly iron and nickel. And the archaeology backs this up beautifully. For example, archaeologists found these ancient beads in Egypt in a place called Giza. They date back to maybe 3,500 BC, possibly even earlier. And when they analyzed them, they found they contained about 7.5% nickel. Now, iron you get from earth ores has hardly any nickel, just tiny traces. But that's 7.5%. That's a dead ringer for the composition of iron meteorites. It's like a cosmic fingerprint. And then there's the famous dagger found in Tutankhamun's tomb. King Tut, remember that? Same story. Analysis showed its blade was made of iron, cobalt, and nickel in proportions that perfectly matched a known meteorite found nearby. It wasn't smelted. It was forged from a space rock. And it wasn't just Egypt. Way up in Greenland, the Inuit people famously used iron from a huge meteorite called Cape York for generations, hammering pieces off to make tools and harpoon tips.
That's incredible. So people were literally working with pieces of asteroids or planet cores that fell to Earth. What was this meteorite iron like to work with, especially since they couldn't really heat it up properly without smelting tech?
Well, that's another key part. This meteoric iron, because of the nickel usually, was actually quite soft and ductile when cold. That means you could hammer it into shape without heating it up much, or maybe at all. Cold forging, that was perfect for early toolmakers before high-temperature furnaces. Interestingly, if they did try to heat it too much, that nickel could make it brittle and prone to cracking. So working it cold was often the way to go. And you have to imagine finding this stuff. It must have seemed magical. It literally fell from the heavens. So this iron from the sky, as some cultures called it, wasn't just useful. It was highly valued, probably seen as sacred or powerful. Its cosmic origin gave it this immense symbolic weight, this mystical quality. It was special because it came from the sky.
What an amazing picture. From stars exploding light years away, creating iron, to chunks of that iron traveling through space for maybe billions of years, then falling to Earth, being found by early humans who recognized it as something special, something workable, long before they figured out how to get iron from the rocks beneath their feet. And only much later, with groups like the Hittites mastering smelting, did iron from the earth start to become common, kicking off the real Iron Age and changing, well, pretty much everything. So there you have it, the unbelievable journey of iron. Forged in collapsing stars, delivered by meteorites, and first picked up by human hands as a gift from the cosmos. It really changes how you think about something so ordinary, doesn't it?
It absolutely does. It's a fantastic reminder, I think, that even the most basic foundational materials of our world can have these incredibly unexpected, truly cosmic origins. So next time you see a steel bridge or get in your car or even just, use a knife, maybe give a little thought to the exploding stars and falling space rocks that started it all. Makes you wonder, doesn't it? What other everyday things around us have hidden stories that are just as surprising?
Absolutely. Well, if you found this deep dive as fascinating as we did, do us a favor and hit that like button, subscribe for more, and maybe share today's aha moment with someone else who loves a good story. We'll catch you on the next deep dive.